Hi, I'm Matt. I'm going to do this non-traditional textbook. It's the Physics of Superheroes. I think it's really good because it covers a lot of basic ideas in science and gives a lot of really good analogies, because I feel like analogies are some of the best ways that we can explain science and math to people, because it's relatable, right? It's making seemingly complex ideas much more relatable, and it's pretty good. It comes from a place of okay, here's how it works physically in the real world. Does this comic book hold up to it, right? And actually, a lot of them do. A lot of them make a lot of sense, which is interesting, because you wouldn't think that superheroes and the real world really go together, but they do. Okay, so I'm going to start up here. When the melter first appeared back in 1963, the notion of melting ray seemed suitable only for comic books, blah, 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 blah. You probably now will have one in your home. You no doubt refer to it as a microwave oven. So, this is really important. I'm going to call this determining importance, because a lot of our ideas that in science come originally from a place of science fiction. And this makes a lot of sense if you think about it, because somebody has to think of it before it can happen. So while that science fiction may not be the same, right? Like in this example, the melting ray and the microwave oven are clearly not the same. They don't really serve the same purpose, but they kind of do the same thing. And you could call them pretty similar objects. And it may not even be causal, as in this example, right? The microwave oven was doubtably designed with the melting ray in mind. But it could also be a source of inspiration, right? In Jules Verne, 20,000 Leagues Under the Sea, he describes an underwater apparatus that later became the first diving apparatuses that we used, right? The ones with the big clunky metal helmets and the hose attached to the back of the head so you could breathe and stuff. That actually originates in Jules Verne. So, that's the importance of that. And a little bit of background knowledge. Okay, and then I'm going to go here. Before we can answer why solids melt when they become very hot, we need to address a more basic question. So, this is part where I kind of disagree a little bit with the book. I think it's a little bit misleading. It says very hot. Well, very hot is a relative term, and I'm going to call this background knowledge, I guess. Maybe some self-questioning going on, because I don't think this book makes a whole lot of sense when it says this. Very hot. What is very hot? Well, very hot could be it's 90 degrees outside. It's very hot. It's 212 degrees on the stove. It's very hot. It's 32 degrees Fahrenheit. It's very hot. Technically, it melts water, right? It melts ice into water, right? Ice is a solid. And by this logic, solids melt when they become very hot. So, very hot is a relative term. Very hot says that the temperature at a solid's point increases and causes it to melt. Okay, so that's that. That's our background knowledge. A little bit of self-questioning. Okay, under certain circumstances, two atoms may have a lower total energy when they are close enough to each other that their electrons' orbits overlap. And when this happens, a chemical bond forms between the two atoms, okay? So I'm picturing two kinds of bonds. I'm picturing sigma bonds, which come together like this, and pi bonds, which come together like this, right? It's interactions like across a gap. And so I have a lot of visualizations for orbitals and molecules in my head but I don't really know how to describe them other than, that's just what they are. It's kind of like, they happen between, or I guess pi bonds happen between mainly p orbitals, which are dumbbell shaped, or d orbitals, which are four-leaf clover shaped. And that's a little background knowledge. And then down here we have one of the best analogies, I think, for phase transitioning. It's easier to hook up a trailer to a towing hitch on the back of a truck if you slowly back onto the hitch rather than smash into it at 100 miles per hour. So that is basically the difference between a relatively low energy molecules interacting with one another rather than relatively high energy molecules interacting with one another. And so this background knowledge and maybe maybe a little extended thinking, is if I have two things that I'm trying to get to stick together, am I better off pressing them gently together or whipping them at each other? Well, I guess it depends on technically what it's made of, but most of the time you're probably going to go for the gently press and maybe firmly apply, right? Think of sticking a poster to a wall. And then the last thing I want to do is talk a little bit about how I think analogies are helpful. So when I think about ideal gas law, right, like pressure and volume and temperature and how they interact, I like to use the analogy of a balloon, because balloons are really easy for people to understand. So I can say, what happens to a balloon when you sit on it? And people might say pop, but I'm specifically thinking of the size of the balloon. What happens to the size of the balloon when you sit on it? Well, it gets a lot smaller, and that's because you're increasing the pressure. So the size of the balloon gets smaller, which means the volume is getting smaller, and you're sitting on it, which means you're increasing the pressure. So the pressure goes up, the volume goes down. That analogy right there just described to you the perfect interaction between volume and temperature, right? Their relationship. Volume and pressure, their relationship, they're inversely related. One increases, one decreases. This is the shortest I could get this video to be. I'm really sorry it's already 7 minutes long. Thank you very much for watching. I hope this was informative in some way.